Okay. So anyway, so this is work done with all these people. I mean, I think most of them are not here. I don't know if Satyam is here. Oh, he's there. Okay. Then okay, so Rekha is somewhere in Japan. Junaid is somewhere in Kashmir, and Diptiman and Shankar, they are somewhere. Okay, so so let me try to explain what the basic problem is. So since it's a broad audience, I thought I'll just give some very quick introduction. So basically, we are looking at quantum Hall effect. So basically, supposing you have a 2D sample, some metal, and there's some magnetic field that you apply into this here. So this is some 2D metal, and then let's say I connect it to leads. Okay, so so leads with some battery, which there's some different chemical potential, mu plus delta mu and mu here. So there will be some current. So some current will go. So let's call it Ix. And because there's a magnetic field, I mean, they will kind of move this way, right? So this will induce some charges to accumulate out here, and there will be some voltage difference, and let's call that V of Y. Okay, so this is the observation, and if you put a voltmeter out here, you will get some voltage difference. So you can define what's called a transverse conductance G of xy, which is the current in this direction divided by the voltage in this direction. Okay. So equivalently, this you can show it's the current density divided by the electric field in y direction, and so this is also equal to the conductivity. So this is the transverse conductivity. Okay, so now so this, of course, you can measure it easily in a lab, and this was known already. Hall effect was known for a long time, and what was interesting is in 1980. Von Klitzig did an experiment where he found that this number, this quantity in some experimental regime is quantized. Okay, so it's quantized in square by 8. Okay, so okay, so this is basically you can just take a free like non-interacting electrons, and you need a magnetic field. But then afterwards, people discovered that even without a magnetic field, you can get this effect. So this is called anomalous quantum Hall effect. And basically, you need a system which breaks time reversal symmetry. Okay. So okay, so I'll be mostly talking about this kind of system, and the simplest example of this is something called spinless BHZ model. Okay, some people Barnevik, Hughes, and Zhang. Okay, so in this model, basically you think of a, let's say there's a square lattice. Okay, and on each side there's a two-component wave function, so psi1 and psi2. And then there's some coupling in this direction, some coupling in this direction, and some on-site potential. Okay, so this is the model. And okay, so I'll write down the Hamiltonian later for this system. But there are two degrees of freedom at each side. So if you compute, so the simplest thing you can do is compute the spectrum of this system. So you can compute the spectrum, let's say on a like if you put periodic boundary conditions on both sides, and you'll find that there are two bands like that. Okay, and there's a gap. Okay, then you can also put the same system, supposing you consider like a strip, so it is open on both sides. Then you'll find that so apart from these two bands which are unchanged, there's also some set of states like that, and these are known as because there's no time reversal symmetry. This system has what are known as chiral modes. Okay, so there are some eigenfunctions which support a current and which live right on the edge of the system. Okay, so I mean the same system, you just change boundary conditions, you get this new set of edge modes. So these are the okay. Then if the same system, supposing you put it on a if you consider a cylinder, then you'll find that there's one more branch So there now you can have edge modes out here and some edge modes out here, okay, which have opposite chirality. Okay, and this give you this set of states on the edge states in the spectrum. Okay, now, this system again, if you put leads, you'll find it's quantized. And how do you understand it theoretically in terms of like the topology of the system? So there's a famous result which is called the TKNN result, which relates the conductivity to some topological invariant. Okay, so given this, let's say I take this kind of geometry. So I have eigenstates which are labeled U bar. So I can just do Fourier transform in both directions, and I'll get wave functions which depend on a wave vector and has two components. Right. Now from this I can construct what is known as a Berry potential, which is just take the wave function and take a gradient with respect to the wave vector. Okay, and maybe there's a minus I factor. Okay. So you can construct this vector potential. So this is derivative with respect to the two k's. Okay, so I get a two-dimensional vector. Then from this I can construct something called a Chern invariant, which is integral over d2k. Okay, and what, so this is some quantity I can just construct using just the eigenstates of the isolated closed system. Okay, so what these people showed is that you can relate the conductivity to this Chern number. Okay, so this is a very nice result which tells us why this sometimes get quantized, because this is a number, this is an integer number. So this you can show that this is always an integer. It can be 1, -1, and 0 for this model. And depending on the parameter regime, you'll get quantization. Okay, so now what the question we are asking is if you take, those results are everything for a closed system. And the question we ask is, okay, so supposing you look at this geometry, we have this SPH. So this is what I'll call a Chern insulator. And I connect it to leads. Okay, so these are metallic leads. Okay, so, and then I put some chemical potential difference. Okay, okay, so in this geometry now, I put a potential difference. So what will happen is, okay, so here I know that, I mean, there are these edge currents, right? And if I put different, different chemical potentials on the two sides, this edge channels will get populated in different ways. Okay, so therefore I can generate a net current in the y direction, and I can get a Hall conductance in this setup. Okay, so this is kind of very similar to what was. So I mean, to understand this quantum Hall effect, there were some early papers by Laughlin and Halperin. Okay, which kind of actually discuss this setup. Okay, and they had some arguments of like why this kind of thinking about this geometry could lead to us to understand why it's quantized. Okay. So now we want to understand this in a more detailed way, this setup. Okay, so let me now go to the main results. Okay, maybe I'll just go through this. Okay, so this is about how much time? Oh, 14 minutes? No. What is it? How much time do we have? Oh, really? Oh, great. Okay. Okay, thanks. Okay, so okay, so this I already discussed that you can define this Berry potential, and then this is the Chern number, and this is the famous TKNN formula. Okay, and so this is the model that we are that I'm studying. And so, like I said, if you are looking at a completely periodic boundary conditions, this is a spectrum. There's a big gap. But if you're on the strip geometry, you'll have this set of extra states. And this Chern number can, depending on this on-site potential, you can have different Chern numbers. Okay, so now this is, we connect it to this left reservoir and right reservoir. And in the reservoir, it's just a simple square lattice. So there's a spectrum which looks like this. So, so this eta x is the coupling in the x direction, eta y is the coupling in the y direction. So this is, these are the parameters in the leads. And out here, there's some coupling which is eta c. Okay, so now the question is like, I mean, when I look at this conductance, does it depend on all these parameters? Okay, I mean, does the lead play any role in changing quantization? Okay, so first of all, this geometry is nice because you can just do in this y direction, there's translational invariance. So you can just do Fourier transform in y direction and you can get an effective one-dimensional model. Okay, so this is some well-known model called Rice-Miller model, which looks like this. So at every side, there's a two-component wave function. And then there's some sort of coupling, there's some on-site potential A, and there's and there are some other couplings. So now for this model, you can do this formalism called NEGF, non-equilibrium Green's function, and you can compute the Hall conductance. Okay, so Hall conductance means what is the current in this direction, y direction, because of applied field in the x direction. Okay, and this is what we observed. I mean, you find nice quantization. Okay, so now we want to understand this. And one very nice way to understand this is by looking at scattering states for this system. Okay, so now the scattering states are very simple. Okay, in the y direction, it's just plane waves. And in the x direction also, it's there's an incident plane wave. Then this is the reflected part. And then inside the insulator, because we are looking in the gap, it can't transmit, so it decays exponentially. Okay, so this is the wave function in the insulator. Okay, so now, I mean, this is a simple 1D problem, so you can explicitly solve the scattering problem and find these coefficients. In particular, since there's no transmission, so this R, mod of R has to be 1, so it's a pure phase. Okay, so it's just e to the power I chi. Okay, now given this scattering state, okay, so I mean, the non-equilibrium problem is basically like you have this Chern insulator, and the reservoirs, I mean, you can just think of them as non-interacting fermions. So if you find like a given fermionic state, how does it behave? First, we have to find that, and then you have to think of the reservoir is the sending this different fermion states from some thermal distribution, right? You have to sum over all those states. So this is one state, and then afterwards we have to sum over all possible states from the thermal reservoir. Okay, so for given one eigenstate, you can compute like what is the y current, and this current you can compute it both in the metal and in the leads. Okay, so in the leads, it decays exponentially because you can't, I mean, there's a band gap, so there are no states in the lead, so the current decays exponentially, while in the metal, of course, it's just oscillatory, right? Okay, so now we have to integrate over all the allowed states, so all states on the Fermi surface. So the states are labeled by Q and K, right? These are the two momentums. Q goes from 0 to pi because you can only have right movers, and K is, of course, minus pi to pi. Okay, so you have to do integrate over all this momenta, and after doing some, you get these are the Hall conductance in the leads, in the metal, and in the insulator. Okay, so now what is interesting is that if you plot this, you find that there's a Hall current even in the metal. Okay, so even though this is the Chern insulator, and you expect a Hall conductance inside this, but somehow this induces a Hall current even in the metal. Okay, so there's a Hall current which actually decays as a power law in the metal, and in the insulator it decays exponentially. Okay, so this is what we call the proximity effect. The Chern insulator induces a Hall current in the metal. Okay, then you can integrate over all the currents, and then you just find the total Hall current in the generated in the entire system, in the leads plus in the metal. And then what we find at the end is that quite miraculously, it's just given by, it's a total derivative, and it just depends on the phase of the incident beam. Okay, so maybe I'll just end here. Okay, and I mean, individually the metal and Chern insulator, they are not quantized, but when you add them, it's perfectly quantized. Okay, so maybe I won't explain this, but basically we can compute the Berry potential, which is quite for the entire scattering state. And again, you can show that the Berry phase is directly related to the conductance. Okay, so I'll just show my conclusions. Okay, sorry, I read. Thanks for the extra time.
So do we have any questions here? You have a mic? Yeah.
That how much these results are like robust in the sense that if I had impurities in the metal, so will these results?
Yeah, impurity is robust under impurities. Okay, that's difficult to prove analytically, but numerically we can check that if you put, I mean, it's like quite large amount of impurities, it's still quite robust.
Me, what were the parameters in the system and how the decay length, like on what parameter does that depend?
Okay, that's a good question. Okay, so the parameters are, okay, so in the leads, there's eta x and eta y, which are the coupling in the x direction and y direction, right? And then there was this eta c. Okay, so these are the, which is the coupling to the Chern insulator. Okay, so this is a Chern insulator. And in the Chern insulator, there is another parameter which is on-site potential. Okay, so these are the main 4 parameters. So normally, if you just thought of the isolated insulator, then depending on the value of mu w, you can be the topological or non-topological. Okay. Once you have this coupling, then things depend on these 3 parameters. And what we find is that even when the isolated system would predict that it should be quantized, but for some values of parameters, it need not be quantized. Okay, but yeah, these are the parameters which determine everything now. So the details of the leads and coupling also matter.
More questions?
You talked about the proximity effect and how you have Hall current decaying inside the metal as well. Why is it power law in the metal and exponential in the Chern insulator?
Okay, I can't give a physical reason. I mean, we can do a calculation and it comes out. Yeah.
But
okay.
it's still in the band gap for the metal also.
Sorry?
It's still in the band gap for the metal also? Is
No,
that
in the metal, it's no. So
we have all the states.
Yeah, because in the metal, I mean, so let's say this. I mean, these are the insulator, but the metal it's filled up to some complete, some level up to like this, right? So it's, I mean, yeah, it's yeah. And in fact, I mean, this power law also depends on these parameters. Okay, so in some for eta x greater than eta y, it's a power law decay. If eta x is less than eta y, it's a exponential decay. Okay, so it also depends on details. We don't physically understand it.
I see. Thanks.
Any more questions? If anybody has a question online, please unmute themselves. I don't think so, right? Okay, I think that's it. Thank you. Thank you, Abhishek.